Welcome to this lesson on group theory. Today we are going to explore a fascinating and powerful concept called inner automorphisms. We will see how mathematical groups can reveal their hidden internal symmetries without any outside help. By the end of this video, you will understand exactly how this internal reshuffling works. Before we dive into the math, let us build some intuition. Imagine you are organizing a complex line dance. Now, suppose you tell everyone to put on a blindfold, perform their exact same dance sequence, and then take the blindfold off. The dance itself has not changed at all, but the way it was executed had a temporary wrapper around it. In mathematics, this wrapper is called conjugation. You apply a temporary shift, perform your normal operation, and then reverse that shift. This creates a perfect mirror image of the group onto itself. Now that we have a feel for the wrapper concept, let us define it formally. An automorphism is a structural perfect match, or an isomorphism, from a group back to itself. It reshuffles the elements but keeps the exact same multiplication table rules. An inner automorphism is a very specific, built-in way to create this reshuffling, using the group's own elements. Because this mapping is created entirely using an element from within the group itself, we call it inner, as opposed to outer automorphisms, which require outside structural rules. This brings us to the mathematical definition. The inner automorphism function is defined as phi sub a of x equals a times x times a inverse. Let us break this down carefully. Phi sub a represents the function itself, and the subscript a tells us which fixed element we are using as our wrapper. The input to the function is x, which can be any element in our group. The output is the result of multiplying a, then x, and finally the inverse of a. This perfectly models our shift, operate, and unshift analogy. If you change the fixed element a, the entire mapping shifts. Before we prove any general properties, let us see this with a concrete example. Let us see what happens when we apply an inner automorphism to an abelian group. Remember, an abelian group is highly symmetric, meaning the order of multiplication does not matter. We start with our standard definition, a times x times a inverse. Normally, we would be stuck here. However, because the group is abelian, we are allowed to swap the order of any two adjacent elements. We swap the a on the far left with the x, bringing a and a inverse right next to each other. Continuing with our abelian group, we now have a multiplied by a inverse. Whenever an element is multiplied by its own inverse, they cancel each other out completely, leaving simply the identity element, e. The complex wrapper has collapsed. Finally, multiplying any element by the identity element just leaves the element unchanged. The final result is simply x. This proves a massive concept. In an abelian group, every inner automorphism does absolutely nothing. It is just the identity map, showing that abelian groups have no hidden internal reshuffling. Now that we have seen an abelian group, let us look at a group where the order of multiplication does matter, such as the symmetric group S3. This group represents all possible ways to shuffle three items. Let our fixed wrapper element be the permutation 1, 2, which swaps the first and second items. We want to see what happens when we apply our inner automorphism to the input element 1, 3. We substitute these specific permutations into our formula, being very careful to keep them in the exact right order. Moving forward with our calculation, our input 1, 3 is now sandwiched between 1, 2 and the inverse of 1, 2. To solve this, we first need to resolve what the inverse of 1, 2 is. As we established, doing a swap twice returns things to normal. So the inverse of swapping the first and second items is simply swapping them again. The inverse is itself. We replace the inverse term, leaving us with the product of three permutations, 1, 2, 1, 3, and 1, 2. To find the final result, we must multiply these three permutations together, from right to left, tracking where each number goes. Starting on the right, 1 goes to 2, the middle term sends 2 to 2, and the left term sends 2 to 1, so 1 stays 1. Next, 2 goes to 1, then 1 goes to 3, then 3 goes to 3, so 2 goes to 3. Finally, 3 goes to 3, then 3 goes to 1, then 1 goes to 2, so 3 goes to 2. The final result is the permutation 2, 3. The element was actually moved to a new location, proving non-abelian groups have rich internal symmetries. So we have seen how the formula works in practice. This brings us to an important proof. To prove that this sandwiching process actually creates a valid automorphism, we must show that it preserves the group's fundamental structure. In mathematical terms, this means proving the function is a homomorphism. We want to see if the function respects multiplication without breaking the rules of the group. To do this, we simply replace our single input variable with the combined product, x times y. The outer wrapper elements A and A inverse remain exactly the same on the outside. This sets up our initial equation. Now we use a very clever mathematical trick to split this expression apart. We can always multiply by the identity element, E, because multiplying by the identity changes absolutely nothing in a group. We secretly slide this invisible E right between the x and the y. This does not alter the value or meaning of our equation at all, but it gives us room to work. Next, we rewrite that invisible identity element in a very specific, useful way. We know that any element multiplied by its inverse equals the identity, so we replace E with the product of A inverse and A. This creates a necessary bridge between the left side and the right side of our expression. Because we are working inside a group, we are allowed to regroup our parentheses however we like. This property is called associativity, meaning the grouping of multiplications does not change the final result. We group the first 3 terms together and the last 3 terms together. Suddenly, 2 familiar patterns emerge from the long string of variables. The first grouped part is exactly the definition of our function applied to x. The second grouped part is exactly the definition applied to y. This gives the final result. Phi a of xy equals phi a of x times phi a of y. We have successfully proven that the mapping is a valid homomorphism. Now that we have proven the structure is preserved, let us visualize this mapping. The diagram you see summarizes what we just proved mathematically. The function phi a takes every single element in the group G on the left, like x and y, and maps it to a new location in the same group G on the right, based on the wrapper element A. Because it is one-to-one and onto, no 2 arrows point to the same destination, and every destination is reached. The structure is perfectly preserved. This beautiful mathematical structure actually has profound implications in the real world. Why do we care about inner automorphisms? They act as a mathematical measuring stick for how non-commutative a system is. As we saw, if a system is perfectly commutative, they change nothing. In physics, particularly in quantum mechanics and particle physics, these conjugations represent changes in the frame of reference or gauge transformations. For example, rotating your coordinate system in 3D space is mathematically described by an inner automorphism, ensuring fundamental laws of physics remain identical regardless of your perspective. Let us summarize what we have learned today. An inner automorphism is a structural reshuffling of a group created by conjugating every element with a fixed element from that same group. It acts as a mathematical wrapper that temporarily shifts the perspective, applies the operation, and shifts back. By studying these mappings, we can deeply understand the internal symmetry of a system, revealing the hidden complexities of non-abelian groups while confirming the rigid simplicity of abelian ones. You now have a solid understanding of inner automorphisms.